This video is a basic introduction to programming in machine language, also known as assembly language, on the Apple II. I'll show you how you can easily teach yourself to program in machine language using the Apple II's built-in monitor program so that you don't need to worry about the fuss and complexity of using an assembler, which might be a hurdle for some. The Apple II has a built-in monitor program. It's called a monitor because it allows one to examine or monitor what's happening inside the computer's memory. To access the monitor program, one can issue the command call -151 from the basic prompt. This puts you in the monitor, which is denoted with an asterisk prompt. From the monitor, you can examine the contents of the Apple II's memory or enter values into it. You can also disassemble machine language programs in memory. Machine language is not really a language in the sense of BASIC or Pascal or C, but rather the raw instruction codes that are performed by the 6502. These codes are actually processed by the 6502 at the bit level and act on the logic gates inside the CPU. But that's a bit much for this presentation, so we'll go over that in a future video. Machine language code can be examined from the monitor by simply entering the address or address range and pressing return, like so. The values displayed by the monitor are all in hexadecimal, a base 16 numbering system. If you have not yet mastered hexadecimal, you should take some time to do so. It's not difficult. All you need to know is that instead of counting up to 9 before carrying to the next digit as in decimal, hexadecimal continues after 9 with the digits A, B, C, D, E, and F, then carries to the next digit. A represents the decimal value 10, B represents 11, and so on, up to F, which represents 15. So when we add 1 to F, this results in a carry to the next digit column. Therefore, the value 10 in hexadecimal is 16 in decimal. Conversely, we can enter values into the Apple's memory by specifying an address, followed by a colon, then the value we want to store in that address. If we enter more than one value, each value will be stored in the next successive memory address after the starting address we specify. 6502 machine codes are assigned 3-letter labels called mnemonics, which makes it easier for humans to code 6502 machine language. These mnemonics are what is referred to as assembly language. Writing in assembly language requires an assembler program. Some versions of the Apple II monitor have a built-in mini-assembler, but in this video I'll be focusing on writing simple machine language programs by entering the actual machine language codes into memory via the monitor to make it accessible to everyone. This is how I learned how to program machine language when I was a teenager. We can use the monitor to disassemble the short program I entered earlier. To do this, we enter the address where the program starts, in this case 300 in memory, by typing 300L and then return. L is the command to list the assembly language code. The disassembly, or listing, shows 4 distinct columns of information. On the left, we have the addresses showing where each machine language instruction resides in memory. Next, we see anywhere from 1 to 3 hexadecimal values. This is the actual machine code. The third column shows the assembly language mnemonic, which is translated from the machine code. And on the right is the data or address upon which that instruction will operate. Depending on the instruction, some require an 8-bit value to be specified, others require a 16-bit value, which is a memory address, and some require no data at all. Notice here that all values are printed in hexadecimal, which is denoted by the $sign. The 6502 has what's called an accumulator. The accumulator is basically the center of the action in the 6502. The accumulator holds an 8-bit value, which can range from 0 to 255, or in hexadecimal, 0 to FF. This 8-bit value can be specified directly, added to, subtracted from, or have its bits shifted left or right. I'm going to keep this introduction simple, so we won't be going into those operations in this video. You can really think of machine language as just moving data around inside the computer's memory. Anything and everything you want to accomplish is based on this simple concept. It is through the accumulator that data is moved around. The 6502 also has 2 registers, X and Y. These registers are like the accumulator in that they hold a single 8-bit value, again from 0 to FF. They are used primarily for keeping count but are also used in more complex instructions such as for indexing and offsets. We'll discuss those more advanced features in a future video. Let's take a look at the short program I entered at the beginning. This program uses existing routines in the Apple II's ROM to read the values of the joystick's X and Y axis. The first instruction is LDX, which is short for Load X Register. This is how we set the value of the X register. It has one operand, which is the value we want to set. In this case, we are loading a 0 into the X register. I'll explain why in a second. Looking at the machine code column, notice that the value here, A2, is the code for the load X instruction. Next to the instruction code is the data value, which in this case is 0. So you can start to get an idea of how simple it is to program machine language from the monitor. You just need to know the instruction code, which you can look up in the Apple II reference manual, or in any number of other books on 6502 assembly language. I myself learned from the Apple II reference manual, which was my Bible as a young teenage hacker. The next instruction is JSR. JSR stands for Jump Subroutine. This is like the Go Sub command in BASIC, except instead of a line number, we specify an address in the Apple's memory, in this case, FB1E. Again, looking at the machine code, we can see that the hexadecimal value 20 is the machine code instruction which translates to JSR. And then we can see the 16-bit address specified, except it's entered in what is called Little-Endian format. So it is 1EFB rather than FB1E. The reason why is well beyond the scope of this video, but just keep in mind that when you're entering memory addresses, you must specify them in this format, with the low order byte first, followed by the high order byte. The routine at FB1E will read one of the axes of the joystick. The axis you want to read is specified by the X register. In this case, we loaded the X register with 0, which tells the routine to read the horizontal axis. When the routine completes, it will return to our code here, with the position of the X-axis of the joystick in the accumulator denoted by a value between 0 and 255, or 0 and FF. The next instruction simply accesses a memory address tied directly to the Apple II's internal speaker, which is C030. Whenever this address is accessed, meaning whenever data is read from or stored to it, it will result in the speaker emitting a single click. It's actually a tad more complicated than this in that every other access to the location will result in a click, but for now we can ignore this minor complexity. The true purpose of the bit instruction is well beyond the focus of this presentation, but suffice it to say that it will access the location specified, which for our purposes results in a click from the speaker, and that's all we want. Once again, looking at the machine code values, we can see that the bit instruction has an opcode of 2C, followed by the value of the address we want the instruction to act upon, again written in Little-Endian format, with the low order byte 30 first, then the high order byte C0. The remainder of the program is simply a repeat of the first three instructions, except instead of loading the X register with 0, we load it with a 1 before calling the joystick read routine at FB1E. This tells the routine to read the Y-axis of the joystick. When that's done, we once again click the speaker by accessing its hardware location using the bit instruction. The final instruction, JMP, stands for jump. It's like a go-to statement in BASIC, except again, instead of a line number, we specify an address in the Apple's memory, in this case, 300, which is back to the beginning of our program. This results in an endless loop, reading the value of the X and Y axis of the joystick and clicking the speaker in rapid succession over and over again. Once the program is running, the only way to end it is to press the reset button. When we want to run our little program, we use the monitor command G, which stands for Go. We enter the address specifying the start of our program, followed by a G, like so. So how does any of this even work? How are these complex audio waveforms created by simply reading the joystick and then clicking the speaker? The magic, as it were, is the amount of time it takes to read the value of the joystick. When the joystick is all the way to the left or all the way at the top, this translates to a value of 0 for either the X or Y axis respectively, depending on which axis we're reading. When the joystick is all the way to the right or all the way at the bottom, This will result in a value of FF, or 255. Because of the way the joystick port circuitry is designed, lower values take less time to read, whereas higher values take more time. The amount of time needed to read the joystick effectively acts as a variable delay. So depending on where the joystick is positioned, it'll take a different amount of time to read the value between speaker clicks, which results in a variable frequency being emitted from the speaker. If we hold the joystick to the upper left, we get a high-pitched squeal, because the value being returned is 0, which means the joystick read routine is taking almost no time to return the value. When we hold the joystick in the lower right position, the value returned is FF, which is the maximum amount of time the joystick read routine can take, and this results in a lower tone. The shorter the time to read the joystick, the shorter the time between speaker clicks, resulting in a higher frequency. The longer the time to read the joystick, the longer the time between clicks, resulting in a lower frequency. And that's really it, to get you started at least. Writing a program for the Apple II in machine language is more about knowing what addresses the various components of the computer are tied to, such as the video output, the keyboard input, and as in this example, the joystick and the speaker. Machine language is simply moving data from one memory location and putting it in another. Knowing the various functions of the memory locations is the key to producing complex programs, such as fast-action arcade games or disk operating systems. Knowing the instructions of the 6502 microprocessor and how they operate is another. Over time, with dedication and practice, you too can write machine language programs, which is very satisfying. I hope you've enjoyed this mini Apple II tutorial. If you appreciate it, please give the video a like, or tell me your thoughts in the comments. I'll be producing more videos like this, as well as others that demonstrate cool tricks and interesting hacks on the Apple II that will please beginners and experts alike. So please subscribe to my channel so you can be notified when new videos are released. See you next time.